Okay, so we're back. Let's just start over again. Anyway, if we do inclined plane problems, first one we've done, and then we need to tilt our axis. So you can see I've tilted my X and Y axis, but we don't do that to make it harder. We do that to make it easier, as you'll see. So in this case, I want to find, let's say I have a free body. I'm doing a free body in general, and then we'll look at this specific for a worksheet. But in general, say I'm trying to find force of pull, or say tension in a string, whatever, that's pulling on the box, the weight of the box, the friction on the box, and the normal force, the contact force of the box in the inclined plane. Alright? The reason I put these angles up here is I was telling the kids that if you have angles involved in your problem, the first one usually you're going to call theta. If there's two angles involved in the problem, you'll call the second one phi. And if there's three angles in the problem, you call the third one psi. So I just showed those. Alright, so let's work our way through this. Well, first thing you want to do is usually let's put mg on there because it's straight down. Now I'm doing kind of a generic one here, so I'm not so concerned with lengths, more orientation. So mg is going to be down. And there's my normal force. Remember, normal force is always perpendicular. Mg always points straight down to the center of the earth. So if your paper, assuming your top part of your paper is up, mg is always pointing straight down. I don't care which way you tilt your axis. The normal force is by normal means perpendicular. So it's an old math term, meaning perpendicular to the surface. So normal force is always perpendicular to the contact surface. So let's get those down, and then let's say, okay, there's a little bit of friction back. And I'll call it F sub S because, as you'll find in the problem I'm about to do, that's rolling friction. So rolling friction is F sub S, sliding friction is F sub K. And then let's get the force of, I'll go ahead and call it tension, because on this one, it can be tension if it's a rope attached to this, whatever it is, or it would be a force of pull if it's somebody pulling on a wagon or whatever. But tension, force of pull, a lot of times used. Alright, so now I'm going to switch this to number 3, and this is 3 from this worksheet right here. It's Investigation 7 Expansion 7, alright, on the website. If you don't have it, you should be able to find it there. Okay, so let's see how we attack this. What's coming up here? I'm going to go ahead and solve the problem here. And so the first thing I want to do, if you have a force at an angle, or a vector at an angle, first thing you want to do is make a right triangle out of it. Notice, since I tilted my axis, only one of my vectors is at an angle. If I hadn't, then I would have 3 vectors. If my axis was up and down like this, up and then across, I would have 3 vectors at an angle. That's a lot of work. So since I tilted, I cut my work by what? Now I have to do 1 triangle rather than 3. So I'll go ahead and color that in. Oh, I'm also showing that there's really, okay, we say that the vector is the hypotenuse of a right triangle. It's actually the diagonal of a rectangle, because you're going to use both. But for right now, we're just going to use this triangle right here. So we color that in. So now we're ready to start the problem. Okay. Getting back to, now we're looking at the actual problem 3. And so once you have your free body diagram, the next thing you want to do is your summation of forces. So that's epsilon, summation of. So our summation of forces in our tilted x direction equal to mass times acceleration in the x direction. And notice we're going to get all the tension or force of pull, whatever you call it. We're going to subtract all the frictional force here, and then we're going to get a portion, as Galileo would say, a diluted proportion or diluted portion of the weight down, or as Bill Fix used to say, the weight down the incline. Okay. So let's go ahead. There's our tension minus our full force, friction back, and then we're going to get a cosine of 90 minus theta I. And so, or we could also say this, mg sine theta I. Now a lot of you are saying, wait a minute, how the heck can you do that? And that's where we're going to go to another sheet. So let's pause this for a second. And I'll go to another sheet. Okay, so This is the reason why we're using that mg cosine 90 minus theta I, or mg just sine theta I. This is something you've got to just know, because if you have an inclined plane and this is your weight vector down, remember that since it's at an angle to this x-axis, it always makes a right triangle. So my red right triangle is the one that's formed. The two components, there's mgx and mgy. And then the black triangle is just the inclined plane. Alright, now theta I, when you say subscript I, you mean angle of incline. So let's go through this. Okay, now if that's theta I, then that angle up there, that's 90, because it's by definition that's horizontal and that mg is perpendicular. So that has to be 90 minus theta I, the yellow, but then these are corresponding, so that's also 90 minus theta I for the red. And the reason is, remember, three angles of a triangle that up to 180, you got 90 there, so therefore these two, theta I and this angle up here, must be complementary, and therefore they must add up to 90, so that must be 90 minus theta I. Okay, prove that to yourself if you need to. Let's keep going. So if that's the case, and then that's also a right triangle because we dropped it straight down. Okay, this is the old x and y component of this vector, so obviously that's a right triangle there. So when you do that, this becomes theta I down here. And so it's really the yellow and the red always form these similar triangles. Not congruent triangles, but similar triangles, because all their angles correspond. So we could call this leg up here is what we're interested in, of our mg. We only want a component of the mg, we want the dilute component of the mg down the incline. So let's take a look. We could call it mgx, that's fine, but it doesn't really help us much in an equation. And so we go through and say, well, it's mg either sine theta I, because theta I it's opposite theta I and opposite over hypotenuse. Remember that this leg over mg equals sine theta I. Therefore, do a little algebra and you'll see that mg sine theta I is the length of this leg. And I don't know, some of you got to go back and prove that to you, because I think all you're doing is copying this stuff down. You didn't take the 5 minutes to sit down with the right triangle and think this thing through. If you do that, you'll stop having to just try and memorize some stuff. I'm serious. 5 minutes with the right triangle, thinking about it, you'll get this, why I call this mg sine theta I. I've shown it to you, but many of you still don't get it because you're not really visualizing it. You've got to sit down with the right triangle and do that. It'll save you a lot of problems later. Well, that's the same thing as saying mg cosine theta I, 90 minus theta I, because these are complementary. Cosine and sine are basically 90 degrees out of phase. Is one way of thinking about it. The other way of thinking about it is, well, here it's the opposite side for this one, here it's the adjacent side for this one. Okay, so cosine means adjacent, sine means opposite. Okay, I think that's all I had. Oh, alright. Alright, so now back to the previous drawing. Okay, now looking at this drawing again, now that we kind of got that cleared up, why that was mg. You can use either one. I don't care. Some of you prefer to stay with cosine because it's x and sine for y. I dig that. That's fine. Others may just want the convenience of just calling it sine. Just realize if you're calling it sine, you could get confused later. It's the one reason why you want to call it mg sine theta is, and there's some of the derivations coming up, it's easier to call it mg sine theta. And a lot of your professors will call it mg sine theta. Alright, so keep going, and that's going to equal max. Okay, so there's the three forces in the x direction. We get two full ones and a component of another. Alright, so now all we got to do, I want to go ahead and solve for a sub x, and just basically the same thing. I'm just going to divide by the mass. Okay, and there it is. Now I can start plugging in. Now I'm ready to plug in numbers. I've gotten as far as I can with symbols, so I plug in numbers. The mass is 40. This is for number 3 on that part 7. So 40 kilograms. The tension is 170 newtons. The friction was 15 newtons. Theta I is 18.5 degrees. And from there on, you can solve the mg. Remember the m up here, that's 40. G is 9.81. So the actual weight's more like 390, whatever. All right. Once you find a sub x, then let's look at a previous. Then you can go back and solve for. See if I did it here. No, one of these I solved for it. It's a then third orange. Yeah. Okay. Maybe up here. No, let's see. I know somewhere I did that. I thought. Oh well, I'm wasting your time. Anyway, then you can plug into your third orange and solve for, because it tells you right here that the delta x is 80. Maybe I never did. Maybe I just talked about it. Okay, so whatever. One other thing, this happens a lot. People, let's get rid of these things. Okay, people think that this is a tilted axis. People think the normal force is like, okay, they get this part right. They get the normal force right, that it's perpendicular to the inclined plane, but then mg they get wrong. Mg always points towards the, remember, mg will always point towards the bottom of your page, so that can't be right. Here they have mg pointing towards the bottom of the page, but then they don't have the normal force. The normal force should be perpendicular, and they have it going straight up. Normal force only goes straight up if you're sitting on a horizontal surface, all right? But if it's on an inclined plane, normal force is going to be perpendicular, and mg is pointed down. So that's why I've marked off those two. Those are both wrong. This is the only one that's right. So that's going to be your standard. It's kind of a setup for inclined planes. All right. There you go.